1 decade ago, the Global Climate Observing System, which is an international board, and it supports the United Nations in their effort to tackle climate change, had put up a list of parameters, like the clinical parameters. When you've got a patient, you want to monitor all of them to tell the health state of that patient. And there's this list of critical parameters that we need to measure. They're called the essential climate variables. And guess what? From space, from satellites, we can monitor many of those parameters and get a very good estimate of those. You will have seen examples for ocean color or sea surface temperature, and in particular, the rise in sea level that we see from space. This is really a crucial parameter, an indicator of climate change on our planet. And the European Space Agency has launched already 5 years ago the Climate Change Initiative to monitor essential climate variables from space. This is the result of the Climate Change Initiative for sea level, but then there are similar results looking at sea surface temperature or ocean color and other parameters. For sea level, what people have done working into this huge project led by CLS of France is looking at the data, making the data more accurate, improving everything that was possible in the various corrections and in the various algorithms that you use to extract the information from the raw data, so that you would get a better estimate, you would get more accurate estimate of the rise in sea level and have more confidence in what you see. Of course, there's quite a lot of work that involves integrating these kind of measurements with in situ measurements, which remain important, like measurements from tide gauges and measurements from floats like the Argo floats. So it's not just space, but space will give you the global picture and satellites will give you the global picture, and in combination with the in situ data you get the accuracy that is needed for this kind of application. This is also important because we are really now starting to benefit from many years of investments by European taxpayers into satellites, but we can now use those data to see what is going on in the long term. We've got 20 years of data from satellites alone, and we can confirm that we are seeing a steady increase of sea level at 3 millimeters per year.
So this Glob Albedo data product was produced from a range of European Space Agency sensors over different time periods and different spatial resolutions, which is one of the challenges of producing products like this, of merging these different data sets. And so this particular data set included data from the SPOT VGT sensor, from the MERIS sensor, and from the ATSR family of sensors. And the approach that was taken was developed in such a way that when new observations come on stream from the Sentinel program, for example, they can be incorporated into this processing chain, and we can extend this global production, so beyond the present day and into the future as we collect and collate new observations at different time and space scales. A product like this was developed in response to a number of different requirements, but one of the chief requirements for this was the ESA CCI, or Climate Change Initiative. And essentially that identifies a number of key observations that are required for understanding climate change and asking the scientific community to define what those observations might be, the precision of measurement of those observations that is required in order to improve our understanding, and in essence to define the kind of parameters that we should be measuring and that we should be targeting, if not now, in future when we develop new sensor programs and systems. And so that kind of approach means that we're looking very much at developing long-term continuity of sensors and observations. And so a very good example of this takes various observations that have been made over the last 10 or 15 years by a variety of different sensors, such as the MERIS and other instruments on board the Envisat platform, and says, okay, can we carry on the legacy of those instruments in such a way as the observations can be seamlessly integrated over time and space, and then even better, augmented with other observations that have improved capabilities in terms of the wavelength resolution, in terms of the space and time resolution.
The Climate Change Initiative programme is very useful in bringing together all the international expertise in different types of data from across Europe. And the purpose is really to be able to go back in time, look again at data that were collected over the several decades, and bring them up to a standard that can be used for climate studies. For climate, you need to be able to compare, for example, the sea surface temperature from one year with another year, maybe 20 years before. This is not what these sensors were originally designed for. And so in the CCI, we use a range of techniques to bring that degree of comparability across time, which is required for climate studies.
Previously, we've had ocean colour data from 3 or 4 different satellites. You can't directly compare the information that you're getting from each of those satellites, and that's because they're slightly different instruments, they have slightly different characteristics, and they use algorithms which are slightly different to extract chlorophyll. So one of the really important things that the CCI has been doing is to try and make all of those data sets consistent. So to make a data set which we can reliably know that if we see a change in the data, it's genuinely due to a long-term trend and not to some artifact because of a change in instrumentation or satellites. One of the important developments recently with the ESA Climate Change Initiative is that they're not just taking the satellite ocean colour records, but they're also integrating those observations with other in situ data, such as from ships, for example, or increasingly from autonomous technologies such as moorings, floats, etc., which give us real estimates of chlorophyll concentration in the ocean, which we can then use to validate our satellite data. We currently have about 16 years of satellite ocean colour data. That's been absolutely revolutionary in our understanding of how phytoplankton populations change. That's mostly in response to natural variability. So the same way that plants on the land go through a seasonal cycle, they bloom in spring and die off in autumn, so do phytoplankton, the plants in the ocean. So the satellite data has been able to tell us about that aspect, but it's also been able to tell us about longer term change as well in the context of climate change. Unfortunately, 16 years of data, it sounds like a lot, but when you're trying to look at a long-term change as climate change is, it's really not enough. And some recent research that we've done has demonstrated that actually you need more like 30 years of continuous ocean colour data to see a long-term trend. And that's because the natural variability in phytoplankton is really large. Unfortunately, if the satellite record for some reason is broken, perhaps a failure of one or more satellites, that actually increases the amount of data that we need to see that climate change trend. It increases from around 30 years to around 60 years of data. So I'll be in a retirement home by then, so I don't want that to happen. So it's really key that we can keep these long, continuous, consistent records going.